So, Google just dropped some huge news in the world of quantum computing. They're claiming an achievement that honestly could completely rewrite the rules for how we solve some of the planet's most difficult problems. Okay, let's get right into it. It really all boils down to this one single number 13,000 times. Now, that's a massive figure, right? But 13,000 times what? Get this. It means their brand new quantum processor ran a specific calculation, a real-world calculation, 13,000 times faster than the most powerful supercomputer we have. Period. That isn't just a step forward, it's a colossal jump. So what did they actually do here? Because this is not just some abstract test in a lab. No, this was a practical demonstration. They used their new quantum processor, which they've named Willow, to get the job done. And that brings us to this absolutely crucial idea, practical quantum advantage. You know, for years, this has been the holy grail for everyone in the field. It's not about just being fast for the sake of being fast. It's about proving a quantum computer can solve a useful, real-world problem better than any normal or classical computer ever could. The actual problem they took on was a monster from the world of physics, trying to model how information gets scrambled up inside a really complex quantum system. We're talking about a system where all the particles are entangled. Their fates are linked together no matter how far apart they are. It's kind of like trying to track a single drop of ink the instant it hits the ocean and spreads out everywhere. That level of complexity is just a nightmare for classical computers. Now, if you've been following this space for a while, you might be feeling a little bit of déjà vu right about now. And you know what? You'd be right to ask that. Didn't Google make a huge splash about a quantum breakthrough a few years back? Yes. Yes, they did. But what they've announced now is fundamentally different. And that difference is everything. So let's look at this side by side, because this is the key. Back in 2019, they were talking about quantum supremacy with their Sycamore chip. The whole point then was just to prove that a quantum computer could do anything, literally any random task, faster than a classical one. The problem they solved was super abstract, almost designed to be weird. But now, in 2025, with the Willow chip, the goalposts have moved. The mission is practical advantage, solving a useful, real-world physics problem. See the shift? It's from an abstract flex to a real application. So how in the world did they pull it off? Well, the team cooked up this incredibly clever algorithm they call quantum echoes, and it's built around what is essentially a time reversal trick. It sounds like science fiction, I know. The algorithm uses something called an OTOC, or Out-of-Time-Order Correlator. Okay, I know, that sounds super technical, but just think of it as a ridiculously sensitive quantum measuring tape. It's specifically designed to measure how fast information gets jumbled up and spreads out in a quantum system, which, hey, is the exact problem they were trying to solve. And we don't have to guess why they used it. Right in their paper, they say, and I'm quoting here, that OTCs have quantum interference effects that endow them with a high sensitivity. Basically, this method is uniquely tuned to pick up on the tiniest details of what's happening in the system, and that sensitivity is what gives our quantum computer its massive edge. The process itself is just beautiful. First, they let the quantum system evolve normally, run forward in time, let all the particles do their thing. Then they give the whole system a tiny, perfectly timed nudge. And then, this is the wild part, they basically run the movie backward. They reverse the system's evolution. And out of all that complexity and chaos, a perfectly clear signal comes back, the quantum echo. And that echo holds the exact answer they were looking for. And here's the magic. That echo, the final signal they measure, is the result of such a complex dance of quantum interference, it's like trying to unscramble an egg. It is so mind-bendingly difficult for a normal supercomputer to simulate that it would take forever. And that, right there, is where the 13,000 times speed advantage comes from. Okay, so a faster way to solve a niche physics problem is great for physicists. But what about the rest of us? Why does this breakthrough actually matter in the grand scheme of things? Well, it matters because this is a huge step across the bridge from the world of theoretical quantum physics into the real world of quantum engineering. It gets us so much closer to a future where these incredible machines can actually tackle problems that are just completely out of reach for us today. I mean, just think about the possibilities. We're talking about being able to discover revolutionary materials from scratch, like maybe a room temperature superconductor. Or what about designing life-saving drugs by simulating molecules with perfect accuracy? We could create climate models that are so precise they change how we fight global warming. And of course, we can finally start to unlock the deepest secrets of the quantum universe itself. So, look, this achievement isn't the finish line. Not even close. But it feels like a genuine turning point. The era of practical quantum computing doesn't feel like a far-off dream anymore. Which really leaves us with one massive, fascinating question. Once we can fully harness this power, what's the first monumental problem we should point it at?